Building autonomous LLM agents currently traps engineers between two conflicting structural designs, the fragile web and the heavy monolith. On one end, developers integrate directly with APIs. They manually orchestrate LLM calls, tool invocations, and state management. The result is a monolithic codebase where components are tightly coupled, error-prone, and nearly impossible to reuse in future projects. On the other end, teams adopt comprehensive frameworks like LangChain or AutoGPT. These systems are highly capable, but they impose massive architectural overhead and a steep learning curve that dictates exactly how an application must be structured. Both approaches create severe migration friction. If you want to switch from OpenAI to a local Hugging Face model, you have to rewrite your configurations, retune your prompts, and unpick provider-specific logic woven deep into the system. Developers are forced to choose between maintainability and control. This trade-off creates a significant bottleneck for rapid prototyping and deployment. AgentForge is a configuration-driven, modular framework engineered specifically to bypass this bottleneck and prioritize rapid prototyping. This chart compares the core library size of AgentForge to LangChain. AgentForge operates on approximately 5,000 lines of code, while LangChain exceeds 100,000. That reduction extends to dependencies. AgentForge relies on just 10 direct runtime dependencies, compared to 50+ required by heavier alternatives. These metrics define a lightweight architecture, a small core size, minimal dependencies, and a constrained API surface. By limiting the core abstractions to just 3 main classes and 1 backend interface, an engineer can read the documentation and comprehend the entire system logic within a single hour. This simplicity comes with explicit scope limitations. AgentForge is built strictly for single-agent workflows. It lacks native multi-agent coordination capabilities or persistent memory structures. For single-agent workflows, formalizing specific skill abstractions and pairing them with declarative configuration achieves task completion rates on par with comprehensive frameworks, while drastically reducing bloat. The entire AgentForge architecture rests on a single foundational building block, the skill. A skill is defined by a strict formal contract. It is a discrete capability, like web scraping, with explicitly typed inputs and outputs, and a simple toggle dictating whether or not it requires an LLM backend to execute. This diagram shows sequential composition. One skill's output is passed directly as input for the next. A URL flows into a web scraper, scraped text to a data analyzer, and analyzed statistics to a content generator, emerging as a final summary. When multiple skills share the exact same input requirements, they execute via the parallel composition operator. The system runs the skills simultaneously and combines their outputs using a dictionary merge convention, automatically resolving any overlapping key conflicts. With just these 2 mathematical operators, developers can abstract highly complex behaviors into a series of interchangeable, independent building blocks. This modularity is governed by a specific theorem. Sequential and parallel operators alone are sufficient to express any directed acyclic graph of skill invocations. This diagram illustrates a topological ordering, organizing the graph into discrete execution levels. At the first level, source nodes execute via parallel composition. Adjacent levels then connect, feeding the combined output of level 1 into level 2 sequentially. Because the graph is strictly acyclic, meaning it contains no closed loops, the topological sort is guaranteed to complete, ensuring the computation will terminate. As long as the data types match cleanly between levels, the agent's execution is mathematically well-defined. If the inputs and the LLM parameters remain constant, the outcome is fully deterministic. This mathematical bound aligns the API with the structure of a DAG, providing the specific expressive power required for acyclic workflows without adding unnecessary complexity. In practice, building an agent begins in Python. A developer defines a custom skill by inheriting from the core framework and mapping out what data the skill expects to receive and return. If the skill requires generation, the developer does not code specifically for OpenAI or Anthropic. They use a unified LLM backend interface, which abstracts the API provider completely out of the agent logic. This removes provider lock-in. Developers can hot swap between a cloud-based OpenAI model and a local Hugging Face model without changing a single line of skill logic. Orchestrating the pipeline is handled entirely through a declarative YAML file. It isolates implementation details, defining model selection and token limits in one clear block. Below that, a hierarchical list dictates the precise sequential execution order of your skills. It also uses environment variable interpolation to securely pull in API keys, isolating credential management away from the source code. This configuration over code principle removes the need to write redundant pipeline scripts for every new agent, making experimental workflows easy to version control and reproduce. Decoupling the mathematical logic of the skills from the declarative configuration is what allows for the rapid iteration of agent prototypes. To test if this lightweight architecture holds up in practice, AgentForge was benchmarked across standard tasks against direct API integration, AutoGPT, and LangChain. This graph illustrates completion rates for structured tasks. On data analysis and content generation, AgentForge hit 91.2% and 93.8% accuracy, a statistical tie with LangChain. However, on complex error recovery tasks like web scraping and RSS monitoring, LangChain maintained a slight advantage. Manual error analysis showed these failures stemmed from unpredictable website structure changes and strict API rate limiting, where the agent received unexpected formatting and crashed. This exposes an intentional architectural trade-off. By prioritizing extreme simplicity, AgentForge deliberately omits the complex compounding error retry loops and persistent conversation memory found in larger systems. In environments demanding volatile data recovery or extended multi-turn reasoning, heavier frameworks provide a genuine, measurable advantage. But on the execution side, AgentForge's orchestration overhead consistently stays below 100 milliseconds. Total latency is almost entirely dominated by the LLM inference itself, not the framework. Lightweight frameworks sacrifice resilience in unpredictable, messy environments, but they deliver highly competitive accuracy wherever workflows are defined and deterministic. To measure the impact of this simplicity on human developers, an exploratory pilot study tracked implementation and setup times across the different platforms. This chart maps the preliminary findings. The data suggests that AgentForge's minimal API yielded a 62% reduction in prototyping time compared to comprehensive frameworks. By stripping away orchestration bloat and reducing token consumption via leaner prompt templates, engineers spend less time fighting framework abstractions and more time iterating on their specific logic. Again, these lightweight architectures are explicitly not intended to run complex, multi-agent, non-deterministic production deployments. But for targeted tasks, strict component abstraction and modularity provide immense engineering leverage. By treating agent capabilities as formal mathematical contracts and wiring them together through clean YAML files, teams can deploy reliable, single-agent workflows without drowning in framework bloat.